So today I'm going to present some results from experiments that I conducted with Matthew Chantry at Oxford under the supervision of Tim Palmer, who's also at Oxford, and as Sunita said, Peter Dubin, who's at the European Centre for Medium-Range Weather Forecasts. Now in the title I have this phrase, deep learning. There will be no deep learning in this talk per se. Rather, I want to demonstrate that there are applications for deep learning-oriented hardware in other domains of HPC, in this case to accelerate an expensive computational kernel in an operational numerical weather prediction model. So my focus is on the operational setup at the European Centre, and at ECMWF they have a global forecasting model known as the Integrated Forecasting System, or IFS, and it is among one of the most advanced numerical weather prediction models in the world. It is operated primarily in two configurations. So firstly, there is a high-res forecast run at 9 kilometers resolution. This is just a single simulation, so it's a best guess of the atmospheric state. And secondly, there is an ensemble forecast with 51 ensemble members, each one of which has a slightly different initial condition and is subject to slightly different stochastic perturbations throughout the model integration. And this is at a slightly lower resolution of 18 kilometers resolution. As ECMWF goes forward, they are placing more and more emphasis on the ensemble forecast instead of the high-res forecast to reflect the fact that weather forecasting is inherently probabilistic. So the main feature of the forecasting system that's important for us today is the fact that it's extremely time-limited. So they only have one wall clock hour within which to produce both of these forecast products, 15-day medium-range forecasts. So whatever happens, the simulation must finish within an hour, otherwise the forecast product will not be disseminated to the users on time. So the high-res forecast is currently 9 kilometers. This has been increasing gradually over the past 30 years, so it was around 130 kilometers 30 years ago. And in the future, there is a near-term goal to reach 5 kilometers resolution and then eventually go down to 1 kilometer resolution. The reason we're interested in 1 kilometer resolution is because, well, I've chosen to focus here on the representation of convective clouds. We expect the representation of these clouds to improve dramatically as we get down to 1 kilometer resolution, because we will begin to resolve them explicitly instead of having to rely on a parameterization of those clouds where only the mean effect is captured. There are also some other things that we expect to be better represented at 1 kilometer resolution, mostly down to the high resolution of the orography. So for example, orographically forced gravity waves and friction due to those gravity waves. So if you imagine the Alps, for example, how much better that will look at 1 kilometer compared with 9 kilometers. There is a 1 kilometer configuration of the IFS currently under development. The best, I should have mentioned actually that convective clouds, a better representation of convective clouds is also expected to benefit climate projection as well. So people have linked the uncertainty in climate sensitivity, that is how much warming you get from a doubling of CO2. This uncertainty has been linked to the representation of these clouds, and therefore we expect 1 kilometer resolution to also benefit climate projections. So as I said, there is a 1 kilometer configuration of the IFS currently under development. The best performance I've seen so far of this model is around 5 wall clock hours for a 15-day forecast, which doesn't sound too bad. It only sounds 5 times too slow. This, by the way, was run on the PIS-DAINT system here in Switzerland. But this simulation did not include several key components such as the ocean. It was a relatively low vertical resolution, and this was only a single simulation. It was not an ensemble forecast. So when we include all of these factors, the cost of the simulation will go up dramatically, and so there is in fact a significant shortfall between what we can do with the computer now and what we need to be able to do in order to run this model as an operational system. If you want to know more about this 1 kilometer model, you can come see Niels Wiede's talk this afternoon. So we certainly have our work cut out in getting down to 1 kilometer resolution in operational NWP. So the idea behind my talk is that reducing the numerical precision of the floating point arithmetic underlying the model could help us to reach this 1 kilometer target. In the past, double precision has been the go-to, the default precision, And this is because CPUs typically have roughly the same performance between double and single precision in terms of flops. In fact, sometimes single precision is actually slower than double precision. And because double precision, of course, provides more significant digits, there's no reason not to use it. However, in weather and climate modeling, we are increasingly entering a memory-bound paradigm where communication matters the most, whether it's communication between computational nodes in a cluster or between CPU and RAM. And in this computational bound paradigm, when we reduce the precision, we reduce the wall clock time of the model because there's less data to transfer around the system. And so we really have a trade-off here between computational cost and numerical precision. And the developers of IFS have recognized this. They have recently ported the entire model from double precision to single precision. This plot here shows the forecast error of a medium range forecast, and the 2 lines are for the double precision model and the single precision model over 15 days. And you can see the lines are on top of each other, so moving to single precision does not significantly affect the skill of the weather forecasts produced. But as a side effect, the single precision model is around 1.7 times faster, so that's a 40% reduction in the wall clock time. And this speed up really depends on the configuration. Sometimes you get a doubling in the throughput. It depends on how many MPI tasks you're running. I should also highlight some research at Jamstack in Japan, for example. The Barcelona Supercomputing Center and the UK Met Office are all thinking about how we can use single precision to accelerate our models. So going back to the IFS, the ECMWF model, how well does it scale when we go up to 1 kilometer resolution? This pie chart here shows a breakdown of the computational cost of the model as it's partitioned among the different components of that model. It's not exactly 1 kilometer, it's actually 1.45, but it's almost there. So you can see, for example, that the physical parameterizations are around 20% of the cost, as are the dynamics, that's the actual fluid flow computations. But a big chunk of the cost, around 55%, is in what we call the spectral transforms. So the IFS model is a spectral model. The computations are partitioned between a grid point space in latitude, longitude, and height, and a spectral space where the meteorological fields are represented as a sum of basis functions that are spherical harmonics. In order to go between these two spaces, we require the spectral transforms, and they consist of a Fourier transform in longitude and a Legendre transform in latitude. So for the Fourier transform, we have the FFT, which is complexity n squared log n, where n basically corresponds to the resolution, so it increases with resolution. You might be thinking where this extra factor of n comes from. We have to do many Fourier transforms across each vertical level of the model. For the Legendre transform, we typically use a simple matrix multiplication algorithm, which has complexity n cubed. And so as we increase in resolution, the spectral transforms, and in particular the Legendre transforms, become a computational bottleneck. Their relative cost begins to dominate. And this is particularly the case because we have to do these transforms on every time step of the model. And so we want to make them as efficient as possible. I should also mention that there is, in fact, a fast Legendre transform as well. This has complexity n squared log cubed n, which is, of course, better than this, but not as good as the Fourier transform. And so even if we use that algorithm, the same argument applies. It begins to dominate in cost. So I mentioned that ECMWF are using single precision. We could also think about going even lower, down to half precision, only 16-bit arithmetic. Recently, hardware vendors are beginning to make half precision floating point units available. So, for example, the Fugaku computer, aka POST-K, will have native support for half precision arithmetic directly on the CPU, so there's no kind of coprocessor or GPU. And they claim that it will have around 10.8 teraflops performance per CPU. And that's 4 times faster than double precision. And by the way, I also gather that there will be a custom Fortran compiler for this machine as well. So you'll be able to use half precision without having to resort to some other language like CUDA. In addition to that, NVIDIA have been thinking about half precision for many years now. traditionally as a storage format, but also recently with direct floating point units. They have a chip known as the Tensor Core, which is an extremely fast matrix multiplier. That's all it can do. And basically how it works is it's a mixed precision matrix multiplier. So it does the products of the matrix multiply at half precision, but it does the accumulation at single precision. And so you get basically the same precision as single precision, but for a much reduced cost. And they claim that the Tensor Core can deliver around 125 teraflops just for a single GPU, and it's around 16 times faster than doing everything at double precision. So the question is, could we use purely half precision or the Tensor Core to accelerate the Legendre transforms? I mentioned the Legendre transforms are basically a bunch of matrix multiplications that you have to do every time step. And so it seems like an ideal application for this hardware. Okay, so what kind of issues might we expect when we move to half precision? Well, there are two sources of error when we reduce precision. The first is an increase in the rounding error, so half precision numbers have fewer mantissa bits than single or double. And that means that numbers cannot be represented to as many significant digits. Here's an example of what pi looks like with half precision. It's only 3.14. As a corollary, we have to be very careful when adding small numbers to big numbers. If the discrepancy between two numbers is very big, then the small number can be rounded to 0, and therefore the addition will have no effect. The second effect from reducing precision, which is, I think, much more serious, is due to the limited dynamic range of half precision numbers. And so we have to think about the possibility of overflows and underflows. With single and double, we really have ample range for most calculations. The largest single precision number is around 10 to the power 38. But with half precision, the largest number is only 65,504. And just compare this with the radius of the Earth, say, which is around 6,400 kilometers. So if we represent that in meters, then we cannot use a half precision number. And the smallest number is also relatively big, 6 times 10 to the minus 5. So if we have a range of calculations, so some calculations with a dynamic range that extends outside of our representable range, then we're going to get an overflow. That number is going to be rounded to infinity, and the model will eventually crash. In our case, we have a pretty simple fix for this. So the Legendre transforms are linear, which means that if we rescale the input before doing the transform, we can then do the transform using Tensor Core half precision and unrescale the output. And because it's linear, we will recover the exact same result had we done no rescaling at all. And we use this fix in all of the simulations that we show in this paper. It's what Nicholas Higham calls squeezing numbers into half precision. Okay, so now I'm going to present some results of experiments with IFS. I'm going to be focusing on two setups. The first one uses half precision for every calculation in the Legendre transforms. And the second setup uses the Tensor Core, which, is, as I said, was a mixed 32 16-bit matrix multiplier. And I'm going to be comparing these two new setups with respect to a double precision reference. That's double precision for everything. Now, every result in this talk uses software emulation. I don't do any hardware tests. The reason is that porting even parts of the IFS model to relatively exotic hardware like a GPU is pretty difficult. And before we undergo that task, we want to have some kind of assurance that it's a worthwhile thing to do. And software emulation allows us to run these tests on traditional hardware. So this plot shows the difference between the two setups according to the emulation routine. So as I said, half precision uses half precision for everything. And for the Tensor Core setup, we developed this, this emulation technique with help from Visual Meta, our NVIDIA. Basically, we take the input, we truncate it at half precision, and then we do an SGEM, a single precision matrix multiply, and the output is therefore single precision. And we verify that this is correctly emulating the Tensor Core by comparing it with limited computations on a real Tensor Core. As I mentioned, we have to do this rescaling of the input and unrescaling of the output to avoid overflows. We're not so concerned about underflows because there are no divisions in a matrix-matrix multiply. I should also mention that we, of course, have to keep some of the computations at double precision. This is often the case. We find that maybe there's some particularly sensitive calculations in the initialization of the model. I should also mention that the computation of the 0th Fourier mode is kept at double precision as well. If you want to know the reasons why, you can read the paper. But in any case, we do the vast majority of the calculations in the Legendre transforms using half precision or the tensor core as appropriate. So in this first test, I ran a 10-day simulation of the atmosphere using the double precision model. And then with the exact same initial condition, I ran it using the two setups I mentioned, half precision and tensor core Legendre transforms. Now, of course, the error, even though the initial error is 0, because of chaotic accumulation of rounding errors, we should expect these simulations to diverge. And so the error should be non-zero. This error is shown on the y-axis with respect to the double precision reference. And the error for these two setups is indeed non-zero and increases as we extend the forecast. The question is this error that I've introduced meteorologically significant? So weather forecasting is inherently imperfect, and therefore the double precision model does not necessarily give a more accurate weather forecast, even if the numbers are more precise, somewhat paradoxically. So we have to always compare an error with an estimate of our model uncertainty, and that's what I've shown in the gray here. So as a brief digression, I'll explain how I estimated that model uncertainty. At ECMWF, they apply random perturbations to the model to account for the fact that not all of the physical processes are represented. They use a scheme known as stochastic perturbation of parameterization tendencies, or SPPT for short. So the random noise pattern looks a little bit like this. It has a kind of temporal and spatial decorrelation scale. So if we want a good estimate, a rough estimate of model uncertainty, we simply run the double precision model with this stochastic scheme enabled. And that's what I've done. You can see it in the gray shaded area. So in this case, both of the errors that I've introduced are less than this model uncertainty estimate. And so I would argue that the errors are not meteorologically significant. They should not affect negatively the forecasting skill of the model, which is good. So this was an 80-kilometer resolution model. Now I'm going to increase resolution to 40 kilometers. And this experiment is otherwise identical to the one on the previous slide. In this case, the tensor core is still giving good results. The error is less than model uncertainty estimate, but half precision error has increased. So now it's beyond this uncertainty range, which is bad. So what's going on here? I'm going to have to explain a little bit more detail about what the Legendre transforms are in order to show how we can fix this. So the Legendre transforms are performed over many modes from m equals 0, that's the global mean, up to the truncation spectral wave number. It's analogous to a direct Fourier transform where one must evaluate the Fourier transform across every Fourier mode in order to build up a full spectrum. So the low wave numbers represent large scales in the atmosphere, and the high wave numbers represent small scales. Now, for various reasons, the computations at the low wave numbers are more sensitive to precision. Basically, the sums in the matrix multiplication are longer, and so there's more space for rounding error to accumulate. So there's a simple fix. We propose to keep the computations of the low wave numbers at a high precision and do everything else at a low precision. So for the 40-kilometer model, there are a total of 512 wave numbers, and we found that if we only keep the first 10 at double precision, then we get very good results. So that's only 10 out of 511. In other words, we're still doing most of the computations at half precision, but yes, this reduces the error significantly. So going back to the previous plot, the red curve is what I showed before, and the green curve is what we get with this scale-selective precision fix. And you can see it's brought down within the range of model uncertainty, which is good. And I use this fix for all of the remaining half-precision experiments in the talk. So everything I've showed up to now has been relatively idealized. If we want to really evaluate a proposed change to the forecasting system, we need to compare with the real world, with observations. And so that's what I'll do on the next two slides. So I began by running a real Ensemble forecast well, I say real, it actually was after the events took place, so it would be more appropriately known as a hindcast. And the Ensemble forecast had initial perturbations that were actually what took place, what they used when they actually performed this forecast. And I measured what's known as the continuous rank probability score, which is a measure of how skillful the ensemble is with respect to the observations. So we want this score to be as low as possible. And as you can see, it increases over the period of the forecast. Double precision gives basically the same result as half precision, which was quite remarkable for us. The Tensor Core setup gives a slightly lower skill forecast, but I'm confident that with a bit more playing around, I could get all of these curves to match. So I didn't use any kind of scale-selective precision for the Tensor Core setup like I did for the half precision setup. So I'm not concerned that the Tensor Core is statistically significantly worse than the other two setups. So this was a 25-kilometer ensemble forecast. I also performed some high-resolution forecast tests, again verified with respect to real observations. In this case, we just have a single ensemble member. And I averaged the error over around 6 forecast cases. So this is really the headline result of the talk, so I'm going to go through it slowly. We have on the y-axis the root mean squared error with respect to observations. So again, we want this to be as low as possible. And in this case, we have double precision, half precision, and Tensor Core basically all giving the same skill in weather forecasts. And this kind of took me by surprise, because in our field, there's a slightly superstitious attitude towards low precision arithmetic, in particular half precision. And I had this myself, and so I was very surprised that we were able to use half precision all the way up to 9-kilometer resolution, which is the operational resolution used at ECMWF. There are, of course, some slight differences between these curves, but as I said, we only ran 6 forecast cases, and so it's very likely that the differences are within the statistical spread. So the last result that I'll show is a specific forecast case. I'm going to show an animation of forecasts of Hurricane Irma, which hit Puerto Rico in September of 2017. So this top left curve here will be the double precision forecast. The top right is the Tensor Core, and the bottom left is basically what actually happened. We actually ran out of budget, so we couldn't run the half precision forecast, unfortunately. The animation here will look a little bit more choppy because the observations only come every 3 hours, whereas the simulation can do hourly output. And the track forecast will be shown on the bottom right. So if we run forward, you can see that although the two trajectories for the forecast do diverge from reality, the Tensor Core is basically giving exactly the same hurricane forecast as the double precision simulation, which is great. So I'm going to conclude there with some comments. Half precision and Tensor Core can be used in the Legendre transforms up to 9-kilometer resolution. Half precision does not bite, so we should certainly take it seriously. We will probably have to use some kind of scale-selective precision, so keeping some of the more sensitive computations around large scales at a higher precision than the small scales. And finally, although we, of course, introduce an error by lowering precision, this is well within the meteorological uncertainty, the margin of error that we already have. So there's a couple of ideas for future research. Of course, we would like to do some hardware tests. We're thinking about how we can do this at the moment with as minimal effort as possible. And it will probably involve actually looking at the real Tensor Core and seeing if we can actually deliver the speed-ups that NVIDIA claim. But secondly, I think there are certainly other applications for half precision other than the raw computations. And the rescaling technique that I mentioned could really help here. So for example, you could imagine just doing the communication at half precision, so sending the MPI packets with FP16 numbers instead of double precision numbers. And this would require a rescaling technique like what I suggested, but that would allow us to keep the actual computations at double precision and only do the communication at half precision. So I'll finish there, and thank you for listening.
Thank you very much, Sam. That was very insightful. Great talk. Let's open the floor for questions. I see 2 hands. We probably can take 2 questions because we are close to 10:15. So use the mic and press the button. Yes, go ahead.
Thank you very much. In the beginning here, we're talking about gravitational waves. It's quite mysterious because we used to hear about gravitational waves on astrophysics. What do you mean by this?
Yeah, so there's 2 meanings of this term. The one is the waves in the space-time continuum, which obviously doesn't have much effect on how we forecast the weather, at least on a medium-range timescale. Gravitational waves basically refers to the fact that the restoring force for the waves on the surface of a fluid is gravity. So when you throw a rock into a pond, you get gravitational waves spreading out. Yeah, it's an unfortunate coincidence of jargon.
So instead of using half-precision floating point, do you look at B-float 16?
Yeah, we did do some simulations of B-float 16. So B-float 16 is an alternative 16-bit type where you have 7 mantissa bits and I think 8 exponent bits with another bit for the sign. So you trade precision for dynamic range, which sounds great because then you can use half precision without any rescaling or overflows. The problem is the 7-bit mantissa is pretty limited, actually. And in our case, I don't want to rule it out entirely, but we did run some limited tests with a 7-bit mantissa, and we found the error to be substantially higher than any of our other setups that we looked at. A better way forward, I think, would be some other kind of float 16 with, say, a 9-bit significand and a 6-bit exponent. I think that could definitely deliver good results.
Let's take 2 more. This is exciting. Let's do, yes, and then I'll get to you.
So you have been using the IFS version, which is a spectral model,
yeah.
But of course all this load of computation from the Legendre transform is specific to that method. Do you also consider using a grid point model?
Yeah, so people have been ringing the death knell for spectral models for several years now, but they keep on going. Grid point models, it would be more difficult because you don't have this natural separation of scales where you can keep the large scales at high precision, and the small scales at low precision. But we are, in our group, looking at using very low precision in the physical parameterization schemes. And that's an area in particular where there is not really a rigorous justification for using very high precision because some of those schemes are so uncertain anyway. Yeah.
A very nice presentation. You mentioned that just 55% of the whole computations are let's say, in the spectral calculations, and you optimize them. Great job. But from under law, even if you, let's say, reduce it to 0, it's going to have 2x acceleration. So what about the other operations? Are you looking at them? Do you want to port them to Tensor?
So I'm not claiming that this is the silver bullet that gets us to 1 kilometer resolution. It's just one component among a comprehensive plan which involves other technologies like DSLs and accelerators. I haven't looked at the other components of the IFS, and I can't really comment on the feasibility of half precision in those areas.
Okay, just one more, just you. Okay.
So you mentioned that you just said this may get you to 1 kilometer resolution, but giving your results that if you go from the low resolution to the higher resolution, that your error is actually growing, that you're accumulating, and your C probably has to move as well.
Yeah.
So what do you expect for a 1 kilometer range? I mean, is C going to be super
question.
large that you don't have anything left? Because
Yes,
that's what it looks like.
C was 10 for the 40 kilometer model. I didn't actually mention, but I did in the paper, that we did increase C slightly for the 9 kilometer model. So C was 25. In that case, we didn't really bother to tune that, but we found 25 gave good results. So basically, the C divided by the truncation seems to be a constant. And so for T 7999, that's a 1 kilometer resolution. C will be something like 40 or 50. But it's still a much smaller number than the total number of wave numbers. Yeah.
Okay, let's thank our speaker one more time.
Thank you.